We will start with a simple consistency condition on shared registers that is called regular consistency or regular registers. And we will present the algorithm for implementing regular registers. The study for regular register is helpful when we move to stronger consistency condition. In this case, then we will be talking about sequential consistency and linearizability. So let us look to regular register algorithms. We are going to use this notation. 1N algorithm is an algorithm where we have a single designated writer and multiple readers. When we use the notation MN algorithm, we mean an algorithm where we allow multiple writers and multiple readers. When we talk about a single designated writer, we mean a writer for each register. So there could be different designated writers for different registers. So here are the properties of regular register abstraction. We have termination, which says each read and write operation of a correct node terminates or completes, which would mean for each invocation there is a corresponding response of that invocation, and those of course only for processes that are correct. For processes that failed, it might be we have an invocation but there is no response. Then we have the validity property, and the validity property says the following: a read operation returns the last value written if it is not concurrent with another write and not concurrent with a failed write. And a failed write, if you remember, it's a write that starts with an invocation but never terminates, so there is no response event. So if this is not the case, which would mean that the read is overlapping with some write, then it may return the last value written or the concurrent value being written. Termination, of course, is a liveness property, and validity is a safety property. So let us see an example. So this is our notation. We have our processes P1 to P3, and we have a write operation, starts with an invoke and ends with a response. And this is a stretch of the operation. This is a stretch of the operation. So let us see now. So this is operation P1 is a designated writer. It's writing the value of 5. This read returns the value 0, which is correct because the value 0 is the last written value, and this read is overlapping with the write. This read returns a value of 5, which is correct according to the specification, because you are allowed to return the overlapping write or the earlier write. Again, this read is correct, it returns 0, because you are allowed to return the last value written. And this is again is correct, and in this case it is not overlapping with the write, and therefore it has to return the value of 5. The same thing for here. This operation comes after the write operation because the invocation is after the invocation of the read is after the response of the write. So this is regular, but it does not give you a single storage illusion. You can see this here. There is no storage, which is a shared memory storage that does the following. After returning 5, it returns an older value. Regular registers is somehow weaker than what we consider acceptable for a shared memory. We start with a simple centralized algorithm. Here we have a fixed set of processes, and one process is designated as the leader. To read, a process sends a request and asks the leader for the latest value. And to write, a process, which is the designated writer, requests the leader to update the value to V. Clearly, this algorithm is correct according to the validity specification. A process will always read the last value written. However, there's a problem with this algorithm, and the problem of this algorithm is that it does not work if the leader crashes. And in this case, correct processes will not terminate. So we violate the termination property. So now let us try to do a more distributed algorithm. And we start with some bogus algorithm. An algorithm that is intended to implement regular registers, but there is some error in this algorithm. So let us see how we define this algorithm. So the idea is as follows. A read just reads the local value. So a process, when you perform a read invocation, it just reads immediately the local value and returns the result. And a write writes to all processes. So a write request will start a broadcast, for example, a best ever broadcast, and immediately returns. So that is a write. So let us see now. To write a value v, we update the local value to v of that register. Then we do a best ever broadcast of v to all processes. And upon delivery, each process or each node locally updates the value to v and then immediately returns. To read, we just return immediately the local value. So this algorithm seems reasonably. You broadcast and then you only read the local value. So if there is a problem with this algorithm, does it really implement regular registers? The answer is that this algorithm does not implement regular registers. And here is a reason. So process P2 is a designated writer, and P1 in this case is one of the readers. And process P2 immediately does the broadcast and then returns. So this is the invocation and this is the response. The broadcast, of course, takes time to be delivered. So assume it is delivered here at this point. In this case, you can see the following. This read is actually started after the completion of the write. So this read comes after the write, but it does not return the last value written. Neither this read either. These two reads return a previous value, and that does not satisfy validity property of the regular registers. Whereas this read is correct. So we have a problem with this. So here's an execution that does not satisfy the properties of regular registers. So we need to modify this algorithm in a way to guarantee the regular registers property. The basic idea is to make sure that the writer does not return until it knows that the readers have delivered the value that the writer broadcasted. So here is our algorithm. We modify our basic algorithm to use a perfect failure detector P. So we are then in the fail stop model. This is the fail stop model. And here is an outline of the algorithm. To write a value v, the writer updates its local value and then does a best ever broadcast. And in this case, when a process delivers the best ever broadcast, the process then sends back an acknowledgement to the writer. Then the writer waits for acknowledgement from all correct processes. These are only correct processes. We know we cannot use acknowledgement mechanism without just talking about correct processes, which necessitates the use of perfect failure detector. And once it got an acknowledgement from all correct processes, the write returns. The reader just reads the local value. So this algorithm is actually correct. We will show that very soon, but let us see first an example of that. So here is our old example, and so the basic idea was to postpone the write responses. So here is the example that did not work, and here is now our correct example. And in this case, the writer does not complete its write operation until this point. And this is a point where it receives an acknowledgement from process P1. Assume we have no other processes. These are the two processes. And as you can see in this case, that this read operation and this read operation are correct. They overlap with that write, so they are allowed to return the last value written before the concurrent write. So this works fine. The algorithm is simple, but let us again observe certain things about that. So assume, for example, in this case also, that the writer might fail. So it failed here. In this case, the write continues forever. There is no termination. But from this point on, where the failure happened, the reader will always read the overlapping value of the write. So it will read 5, which is again correct according to the specification. So to say it one more time, a writer that failed means that its last write operation will have an invocation but no response. So it's as if the operation is concurrent forever. And therefore, any read that will read that might return that overlapping value or a previous value according to the specification of this algorithm. Now let us look at the correctness of the algorithm. Let us first look to termination. A reader reads a local value, so termination is simple. A writer will wait for acknowledgement of all correct processes, and by the strong completeness property of a failure detector, it will eventually detect failures, and therefore it will wait only for acknowledgement from correct processes, and we assume that correct processes send their acknowledgement by a perfect link, so eventually the process will terminate. Now let us look to validity, and again we are assuming a best ever broadcast, perfect link, and perfect failure detector. So in the case of validity, we have two cases that we have to consider. One case is there we have a process reading, but there is no concurrent write with that process. And in the other case, a process is reading, but there is a concurrent write with that process. So let us take the first case. So here is our first case. No concurrent write with a read operation. So what we do, we assume that it is process P that invokes the read operation. So process P invokes the read operation, and V was the last written value. And this means that the response of the write was before the invocation of the read. So at the time of the read by P, the write is complete. And this is guaranteed by the accuracy of the failure detector, which would mean that P has already stored the value V locally. Just to explain it one more time, the accuracy of the failure detector guarantees that the write completes not early. It waits for all correct processes to get an acknowledgement for them, and then it returns the write response. And that is what we mean that the write is complete at the time of the read by process P. Now let us look to the second case. So the read operation is concurrent with the write of value V. So it's overlapping with the writer writing the value V, and V prime is the value prior to V. So while the writer is writing, the last written value was V prime. We know from case 1 that at this point, each process stores V prime before the write V is invoked. So when a process starts read and read is invoked, so that process either stores V or V prime. It definitely stores V prime, that was the value prior to V, but if the delivery of the broadcast from the writer happens before you invoke the read, then you will read the latest value being written right now, which is V.